Okay, so we're back. We're going to continue with Gauss's law, and we're going to practice using it. Now, again, because we're not going to do any of the heavy calculus with Gauss, we're going to look at some distinct examples. And so all the problems we do will fall into one of these classifications. One will be working with spheres, shells, that sort of thing. So where you have circular geometry. So that's one thing we'll work with. The second will be working with cubes. Again, you have some nice symmetry with a cube. The third would be looking at a cylindrical surface. We like to use cylinders to encircle wires. It's a nice symmetry around a wire. And then we will look at sheets of charge. So those are going to be our 4 different shapes or Gaussian surfaces that we analyze. So in this PowerPoint, we're going to look a little bit at the spherical geometry. We're going to come back to this one because we use it most heavily. Of those 4 examples, we use it most heavily. So we're going to look a little bit at the spherical geometry, and then we're going to do the cube. And so the first set of problems that you have due on Friday of this week look at those 2 shapes and those 2 shapes only. Okay, so this is the first practice problem. And it has 2, so the picture would have come with it. It has 2 distinct charges. You have a point charge, little q or lowercase q, which is equal to 5e, where e is the charge of 1 electron. And then you have a uniform shell of charge. So this is interesting because we have not worked with continuous charge distributions before. So this shell of charge has an overall charge of negative 16 E distributed all around. So you could not use, from back in the last chapter, that E is equal to K Q over R squared. You can't use that equation to find an electric field for a continuous charge distribution because your distance is different all along here, right? If I'm at point P2 and I want to find the electric field at P2, well, part of the charge is here really close, part of it's all the way over here, part of it's here, part of it's here, and so on, symmetrically around this shell. So this equation doesn't work, so I need another tool, and Gauss's law gives me that tool. So the problem says you have these 2 charges, little q, which is just a point charge, and then again, big Q, which is this continuous charge distribution, and they ask me to find the electric field at 2 different points, P1, which is 6 centimeters from the center, and P2, which is out at 12 centimeters, so it's outside of the whole thing. Okay, so let's start at P1. So in the point in question, P1, what I want to do when I apply Gauss's law is I want to draw a Gaussian surface that has that point on it. So because there's clearly some circular geometry here, my Gaussian surface I'm going to draw, so that's these blue dotted lines, hopefully they show up well for you, is going to be right here, the radius of P1. So right here at this radius of 6 centimeters. And I want to find the electric field. So I'm going to take Gauss's law. I'm going to say epsilon naught times the net flux is equal to the charge enclosed. And I can rewrite this as epsilon naught times net flux, which is the electric field, times area is equal to Q enclosed. Okay, so if I think about this, what I know is my epsilon naught, that's at constant value, 8.85 times 10 to the negative 12. I know the surface area of the Gaussian surface that I just drew. This is a 3-dimensional shape. So it's the surface area of a sphere. And I know the charge enclosed by that Gaussian surface. This was given to me. So for this particular surface in the dotted blue, all that's enclosed interior to that is the little q. So if I solve this for E, I can say E is equal to Q enclosed over epsilon naught times A. So E is equal to Q enclosed over epsilon naught times A, which is 4 pi r squared for a sphere. So the charge enclosed is positive 5 times E, which is 1.6 times 10 to the negative 19 coulombs. This is, I don't know if I emphasize this a lot, that's the charge of a single electron. So it's just like a constant you will see a lot. Divided by epsilon naught, which is at 8.85 times 10 to the negative 12. I'm leaving units off because it's getting long. Times 4 times pi. And now the r that I use here is the r of the Gaussian surface. So 6 centimeters, which of course we want in meters, squared. And if I throw that in, I'm being lazy and not using a calculator, I'm cheating and looking at the book. If I throw that in, I get about 2 times 10 to the negative 6 newtons per coulomb. Now, if I used the old, for this one, because this is just a point charge, if I used our old equation, E is equal to KQ over R squared, I'm going to get the exact same answer. Where I change things up is with this second point. Okay, so the second point is outside of the whole thing. And so I draw a second Gaussian surface right along P2. Pretend this is a perfectly round circle. It's not. And I do the exact same thing. So let's just start here at the second line. I say epsilon naught times E times A is equal to Q enclosed. And I solve it the same way. So the electric field is equal to Q enclosed divided by epsilon naught times A, where A is the surface area of this new spherical shell I'm making. And so when I go to fill my things in, Q enclosed, now I have to add the total charge that's enclosed. So I have negative 16E in this shell, and then in the center I have 5E. So my total charge enclosed is negative, and I do put the negative sign in here, unlike the force equations, negative 11 times E, which is 1.6 times 10 to the negative 19 coulomb. And I divide that by epsilon naught, 8.85 times 10 to the negative 12, times the surface area of my new sphere, which is 4 pi, and the R value, again, at this bigger sphere is 12 centimeters, so 0.12 meters, and I need to square that. And when I throw those numbers in, I get an electric field of negative 1.1 times 10 to the negative 6 newtons per coulomb. And again, these signs are important, right? This electric field being positive is saying that it's piercing out. This one being negative is telling me the net electric field is into the surface. Okay, so that's how you would do a spherical shell type of problem. We will, as I said, come back to these and really get into, so I could take it a step further and figure out what's going on the inside surface of this shell versus the outside surface of the shell, and exactly how does this negative 16 distribute itself. So that stuff we'll do later in the chapter, but just as a very broad problem, this is it. The second problem I want to run through, and this will be the last one for this video, is the cube. And we're actually going to revisit the cube that we looked at flux with earlier in the week. So that was the cube with a changing electric field. And so it was a 2 by 2 meter cube. Remember that I told you already, I can't draw cubes, and there's a beautiful one in your book you can look at. But the cube was went from 1 to 3 meters in X, in Y, goes from 0 to 2. And if we want to do Z, which is a 3-dimensional, this would be 0 and it was coming out at 2. We don't really need the Z right now. Okay, so the electric field for this cube was given as 3.0 X in I and 4.0 in J. So this is the electric field for this cube. And so we are going to kind of do the opposite here. So the spherical shell problem that I just did, I gave you the charge enclosed and I asked you to find the electric field at different points. Here, what we're going to do is the opposite. I'm giving you the electric field and I want you to find the total charge enclosed by the cube. Okay, so if I'm giving you the electric field and I want you to find the total charge enclosed by the field, or by the cube, sorry, I'm going to think about Gauss's law. Epsilon naught times the total flux is equal to my charge enclosed. So what I need to do is figure out the total flux of the cube. And again, flux is equal to the electric field piercing the surface times the surface area it's piercing. So for the cube, there are 6 different faces, and I need to figure out the total electric field through those 6 faces. But fortunately, when I look at this equation right here, I can kind of take some shortcuts. So first of all, there is no electric field in Z, right? We have an electric field in X, we have an electric field in Y. There's no electric field in Z, just because there wasn't. And so for two of the faces, like the front and the back face, because those would be my Z, my three-dimensional, the electric field is 0, which means the flux is 0. So that takes care of that. Okay, then we have Y. The electric field is just constant. It is 4 in Y. So that means it's running up. So it's like this, right? So we can go through and find it for Y. We did this actually in the previous PowerPoint, or previous video. But we have the same amount of field lines piercing in to the bottom face as we have piercing out of the top face. Again, because of that constant electric field. So the total flux in Y is going to be 0, right? You have like a negative flux and then you have the same amount positive flux. So the total flux in Y is 0. So that takes care of this face and then this bottom face. So really all we need to worry about when we're finding the total flux is X. The flux is, or I'm sorry, the electric field is changing in X. It's running in the positive direction, left to right. And in the previous video, we found both of these fluxes. For the left face, the electric field is 3.0 times X, which is 1, right? So it's 3.0 newtons per coulomb, times the surface area, which is 4 meters squared. So that gave us 12 newtons per coulomb times meters squared. Now, the field lines were running into, right, just because of the direction, because they're in the overall positive direction, into that left face, which means this is going to be a negative flux. And we found the flux through the right face by taking my function. So if X is 3, that means my electric field on the right face is 9. So 9 newtons per coulomb times the surface area, 4 meters squared, which gives me 36 newtons per coulomb times meters squared. This was a positive flux. Again, I'm going quickly because we already did that. This was a positive flux because the field lines were piercing out of the surface. So for the cube, this is a bit of a mess, but for the cube, my total flux for all 6 faces of that cube is 24 newtons per coulomb times meters squared. Knowing that, I can find the charge enclosed in the cube. Charge enclosed in the cube is equal to epsilon naught, 8.85 times 10 to the negative 12. The unit is coulombs squared divided by newtons times meters squared. Times the flux, which is 24 newtons per coulomb times meters squared. This works out to give you a charge in coulombs. I'm going to just pop over to the book and see because I didn't bring my calculator down. This gives me about 2.1. I'm running out of room. Let's do it up here. 2.1 times 10 to the negative 10 coulombs. This is the charge enclosed by the cube. It's positive, which makes sense because overall I'm going to have lines piercing out, more lines piercing out than in. So I have a positive charge enclosed by the cube. Again, all I did there was find the flux on each surface in question and multiply that total flux by the permittivity constant. So in summary, for just this intro part of Gauss, when we have Gauss's law, we essentially, we really look at it more this way, even though this isn't the formal mathematics. We either are given the charge enclosed and use that to find more typically electric field, sometimes flux, or we're given some information about electric field / flux and we use that to find the charge enclosed. You just go back and forth, right? So again, you're going to practice this first homework set. You're going to be using, there's several cube problems and then a little bit with that shell or circular geometry, and then we'll jump into some of those more complex shapes and really see the power of what you can do with that spherical geometry as we work our way through the rest of the chapter.